and I'm going to talk a little bit about the tools of our trade, microscopes primarily. I think the motivation we have for doing microscopy in general is to visualize biology. And the interpretation can come in many forms. It can come in models, as we saw yesterday. It can come in videos, as we played yesterday, or it can come in artwork, like you see here, this David Goodsell painting of a pancreatic cell where you have insulin staged in yellow, ready to be released. And this is all based on real structures. So despite this being an interpretation, you can build up a systems level model if you can visualize that. And the hope is that not only seeing a static picture, but building it up in a way that you can see biology in action. And that's probably why I like microscopy. And I think one of the most robust forms of the workflow has been our instrumentation. It's come a long, long way since I first started in EM to where we are now. The main thing that we can look at, and I sort of synopsized this a little bit yesterday, is that the scale of biology spans from the atomic level all the way towards the organism level. And we want to access all these resolution regimes. And something that we have done is that we've made use of several different types of sources to access different resolution regimes, from neutrons, X-rays, as well as different types of microscopy, for example, light microscopy. I don't want to make it seem that electron microscopy can do it all, but one thing that I want to really highlight is that electron microscopy can start integrating a lot of these other structural science modalities, and that's very useful because you can bridge different scale regimes. Now, a lot of people are looking after single particle techniques because what we can do in a matter of a few hours is go from raw data to a really useful model and a near atomic model. What has brought about this, and what has brought about this is a lot of hardware and software developments. About a decade ago, direct detectors came out, microscopes became a little bit more user-friendly and stable, and driven by not only the Bitcoin farmers and gamers, GPUs became a lot cheaper, therefore computation became more and more affordable. Along with all these hardware developments came the software developments, and some of these programs you might have heard, from data collection to processing. And what that has done is then what we can do is take a data set that can be quite heterogeneous and pull out a subset that can reach high resolution. Or, as Joachim alluded to, with very, very few particles and asymmetric units, we can start teasing out biochemical states. And all of that has come about within the past decade. And what you can do with that is then not only take the raw data and visualize that in artwork, but really come up with models that are very, very useful. And something that we're trying to do is not only look at macromolecules in isolation, but go into the cell. Now, to point out, electron microscope is very versatile. We can not only do single particle analysis, as this course is really focused on, but tomography and electron diffraction on the same instrument. And let's talk a little bit more about the instrument. The tool of our trade is an electron microscope. It really started about a century ago. In the 1930s, Ernst Ruska and Max Knoll created the first electron microscope. And you can dig in and see some of the early sketches, and you can see what you see in the sketch on the left is very similar to, let's say, the Hitachi that you used yesterday. And even all the way back then, they were looking at biological samples. You can see tobacco mosaic virus here pictured. But why did it take so long to get to where we are now? And a few things that we will now dive into is a little bit more about why we're using electrons instead of light. So one advantage of using electrons is that it has a very small wavelength and we can focus. So just like in a light microscope where you have glass lenses, an electron microscope you have magnetic lenses. Unfortunately, there are a few cons in the sense that electrons can damage your sample and we have poor penetration. As we saw yesterday, we want very, very thin samples during sample prep. So if you have faster and faster electrons, that might be useful for certain aspects because you can look at thicker samples, but you can have more radiation damage on a biological sample. And especially since we're not really staining or protecting the sample and we have it in this vitrified solution, it is quite susceptible to damage. Then the question would be, what types of electron fluxes are we using? We tend to use very low electron fluxes to preserve our sample because we're not really protecting it in that vitrified buffer. And there are a lot of people who have looked at what is the best type of dose to get a really good image. And at a certain point, when you get to hundreds of electrons per angstrom squared, you have quite noticeable radiation damage. And so it depends on what resolution regime you're trying to access. You might be able to get away with a little bit more, a little bit less. If you think of our electron microscope, it's very similar again to a light microscope where we have a source, we have lens systems, and it's a transmission electron microscope we're primarily talking about. So we're going through a sample, and therefore the sample has to be quite thin. If you think about the source, we tend to use electrons accelerated on the order of 100,000 electron volts, 200,000 electron volts, or 300,000 electron volts. So where visible light, you might have wavelengths on the order of several hundred nanometers, and if you use super resolution techniques, you might get somewhere around a couple hundred nanometer resolution. Electrons, we are in picometer wavelengths. Unfortunately, unlike light microscopy, where their numerical aperture lenses are on the order of 1 or 0.9, or you can even have immersion lenses that are even higher NAs. Electron microscopy, our NAs are really poor. They're somewhere around like 1,000th of an NA. So therefore, despite us having picometer wavelengths, we might only be resolving around angstrom level. And that is actually very good because biology is usually around the angstrom level. So what I'll dive into this morning is a little bit about 4 parts of the electron microscope: our sources, vacuum systems, lenses, and detectors. And following me, we'll have Michael Alink, who is our chief engineer here at the Simons Electron Microscopy Center, tell you a little bit more about how we site the electron microscopes and how we maintain them. So let's dive in. So if you go and look at a standard electron microscope, there are several components, from the electron gun to the different lens systems, and we're going to go into that right now. Now, in terms of electron sources, you can think of there are 3 main electron sources that we utilize here at the center. We tend to have sources made from tungsten because it has a really high melting point, and therefore we can use that as very similar to a light bulb. So one of the easiest electron sources is, say, if you have a tungsten filament and you send current through there, you'll kick off a lot of electromagnetic waves. So you'll have X-rays and electrons, etc. And these tend to be thermionic emission sources in the sense that you'll have to heat it up. It takes work to extract electrons from the source. So there's a particular work function. And so if you have enough energy, then you can send out electrons. And we have systems in the sources that can collimate and direct the electrons in a particular way. Other types of sources, you can have a crystal that's a little bit more coherent because you have an ordered array, so you can rip electrons off a crystal. Or what we use more often in a lot of the microscopes downstairs are field emission guns, where we have a tungsten tip that's really finely made. You can see the pictures of the various electron sources down below. In terms of field emission guns, there are different types. We have Schottky FEGs, X-FEGs, C-FEGs, and comparing them to tungsten filaments or what's known as a lanthanum hexaboride source, you can see that if a tungsten filament has a relative brightness of 1, a field emission gun can be several orders of magnitude brighter. And not only that, it can be more coherent. And what I mean by that is that the energy spread is a lot smaller. So on one of our microscopes, we have a cold FEG, and the spread is less than 0.3 electron volts. Whereas if you had a tungsten filament, it could be a couple electron volts. Also, something to think about is that a tungsten filament is only useful for roughly 100 hours. So the Hitachi that you used yesterday, we turn the filament off. We turn the source off when we're not using it. Versus when we have a field emission gun, we leave that on all the time. So they can last for years. I think some of our field emission guns have lasted for more than 5 years, and we've never turned them off. Yep.
So one could call back on all of them instead of just one or two downstairs. When it has more bright.
It really depends on the use case. For a lot of users, they want the throughput. So one thing about a cold FEG, the temperature of a cold FEG tends to be somewhere around room temperature versus the X-FEG. And so what that means is that every so often we need to flash the FEG because they will have contamination. And that, though, despite having very high coherence, some users want higher throughput. So it really depends what you need. So they're all very useful, but you just have to make sure you have the right application. I won't go through the math. What you'll have is tomorrow a lot more math coming from Fred, but you can go to YouTube and you can see, okay, how fast are electrons moving? And this particular clip goes through the math and quite readily. And to really simplify the math, now you would understand why we use electron volts, because if you go through there, that has a very nice conversion. So I'm going to skip this, but suffice it to say that if we have an electron going at roughly 100 keV, you're going half the speed of light, give or take. 200 keV, somewhere on the order of 2/3 the speed of light, and 300 keV, somewhere on the order of 3/4 the speed of light. If you're thinking about how fast electrons are moving, they're moving quite fast. And also, we have exposures on the order of seconds. There tends not to be more than, give or take, 1 electron in the column at any period of time. But since we have such long exposure, it really builds up. Thinking about not just sources, but what type of microscope may be very useful for your application. I think there has been a push to democratize EM, and what that really means is a system that can be widely used for a variety of applications and cited in a variety of rooms. And so a lot of people, Richard Henderson included, have been looking at the regime range of 80 to 120 kV because it's relatively easier to maintain, and the room requirements and environmental requirements are smaller. So traditionally, the 80 to 120 kV range use tungsten filaments or Lab 6 sources, but more and more we have 100 kV FEG systems that are more coherent and can really push resolution. For example, the Tundra that you saw downstairs, we've been able to get 2.5 angstroms with it. So that really opens up the possibilities for a lot of biological research. The 200 kV range has been very useful. So back in the day, if you're thinking about tungsten filaments or Lab 6 sources, you tend to be somewhere on the nanometer resolution range. It's really useful for negative stain. 200 kV, it's more on the order of near atomic. You can push certain systems to get in the 2 angstrom range quite readily. And then if you think about 300 kV instruments, that's the workhorse of a lot of cryo-EM. We tend to be on the order of, near, very, very near atomic, or there have been a few close to 1 angstrom level resolution reconstructions. So it's not yet.
Yeah, I'm just wondering how the highest resolution of laser to the here that you see the highest.
Highest? Well, we can get into the 2 angstrom range. Well, it really depends on the sample. So I'm referring to apiferidin. Okay. Yes, I mean, you can get sub-2. Other places have get sub-2. We're not the Center for Apiferidin Research, so we're not really pushing that. So if we wanted to, I mean, I'm sure we can get, sub-2, but we would rather look at other things. Well, fortunately, we can have a discussion quite shortly after this because we have a few people that are quite knowledgeable. So this particular person is coming from Florida. Yes. Oh, no, we have a few ringers in the back row. But I would have to say that the environment also matters quite a bit. So on our Glacios 2, we have a Spicer field cancellation system. And that has tremendously helped, as you see, because in that room we have 4 microscopes. And that particular microscope has a Selectris and Falcon 4i, and we can really push resolution quite well. Though that form factor is not just a screening microscope, it's a data collection microscope outright. So some people have come to our center not requesting our Krios, but our Glacios 2 specifically for data collection. Again, it's very dependent on what we were talking about yesterday on samples. However, all these microscopes, if you have a very good sample, we're not in material science, they can actually all go subatomic. Unfortunately, our sample can't handle those doses. There are higher keV microscopes. There are megavolt microscopes, and they're very tall. So you saw a Krios that's pretty tall. Some of these are 2 or 3 stories tall. And why would you want to use some of these microscopes? We're alluding to, let's say you have a sample that's thicker than 100 nanometers. Let's say you have several microns. You can use some of these microscopes to have deeper penetration depth. We mentioned that when we were doing sample prep yesterday, we also wanted not only a thin sample, but a sample that can withstand a vacuum. And why is that? Well, if you send an electron through air, it's not going to get too far. You're going to have a lot of energy release within about a centimeter. And not only that, we want to keep our sample very cold. So what we can do is we're not literally submerging our sample liquid nitrogen once it's in the microscope, it's in a vacuum, but through thermal contact, we can keep it quite cold. One way of thinking about it would be if you could take my light bulb analogy. So let's say you have an electron source in, in vacuum, or let's say you don't have it in a vacuum. So you turn on a light bulb without a vacuum, it's going to blow out really quickly. But if you have it in a vacuum, then that electron source or that filament overall will be able to keep on going a long, long time. What that also means is if you think of that light bulb, imagine not only putting your source in a vacuum, your sample in a vacuum, and your detector in a vacuum. And that's really the scenario we have in an electron microscope. Something else that helps with being in a vacuum is we can also reduce contamination. Because if we put everything in atmosphere, what ends up happening is your sample, especially if it's kept under liquid nitrogen temperatures, is a really good decontaminator for the environment. In terms of vacuums, we have several different systems from rotary or pre-vacuum pumps, diffusion pumps, turbo pumps, and IGPs. And we use these in succession. So for example, a diffusion pump or a PVB is backing a turbo pump, and a turbo pump is backing an ion getter pump. So what is an IGP? Imagine just a box with getter material, and you send a few thousand volts through it. If you have any ion in it, it just gets stuck to the side. Towards that end, that getter material can be saturated quite easily. So we want to be somewhere on the order of 10 to the minus 7, 10 to the minus 9 Pascal for our electron sources. And again, that's an analogy is because if you keep your source very well pumped down, then it'll last a long time. So if you're going from atmosphere all the way to the vacuum of where you put your sample, you tend to be somewhere closer to 10 to the minus 4, 10 to the minus 7. So something that happens in reality is that the vacuum is not constant throughout the column of the microscope. You have extra vacuum systems near your electron source to pump it down. Your specimen can be a couple orders of magnitude lower. And then when you get to your detection device, even a couple orders of magnitude lower than that. And what you have between your electron source and the main column where you have a specimen and where you have your detector, you have differential apertures. So the source for, well, I guess more of the modern microscopes are always on. You have your vacuum systems always pumping, but different sections are isolated from each other. When you have the data collection practical a little bit later, you can ask your operator a little bit more about the different menus and then the different vacuum systems, and you can see the array of that. And then when you get to the microscope in particular, you can see how it's all laid out. I think one advantage is that, yes, we're going to go over this in theory, but later in the afternoon when you see an electron microscope, you can dig in. And given that we don't have any users but you can ask your operators to poke in, or we can open up the enclosures. We actually have one Krios microscope under maintenance, and so you can see all the vacuum systems in person. And you can see the space it takes up and what's required to achieve some of these values. Right. And something that people don't tend to think about, you can see such a large column. Lenses are basically this big donut around this size. There's a lot of lead shielding, but the column proper, once you get out of, so what we're seeing is the octagon on the right. If you see that little dot in the middle where the sample is, that's really the column. And you can think about it, if you had the ink from your pen, that's roughly the diameter of the column when it's going through, or what's the electrons going through. In terms of our lenses are actually magnets. We can focus, magnify, and something, if you remember, if you send an electron through a magnet, you think about the right-hand rule. Your electron is not only a particle, but a wave, and realistically, your electron is spitting through the column. And something that the manufacturers have done is that they're very careful on the mag ranges you can use. So if you go to electron microscope, you might notice you don't have continuous magnification. Well, you can, but what will end up happening is your image will rotate. So when you change your mags, you'll notice that there's set magnifications where it helps align and make sure your image is always in the same place. We have a few microscopes where we have extended mag range, and then you'll notice that your image might rotate, or depending on if you're going through different lens systems, it might be flipped. I think Michael will go into this a little bit more, and you can see that in action on how we align the microscopes. But something to make note of is that when you think of a column of the microscope, they're in segments, and we have different lens systems. So there might not be a situation, I'm exaggerating, you might have a segment of a microscope going down here, another going down here. So your optical axis may not necessarily be continuous straight down. So there's several things you can do to make sure that your microscope's aligned and to check the different lens systems. What you'll see a little bit more tomorrow when Fred goes into the math of EM is that the point spread function of an electron microscope can be modeled in the contrast transfer function. And what that means is that the microscope is not perfect. There are aberrations introduced by the microscope itself, and we can model the aberrations due to certain factors and intrinsic values of the microscope, and we need to do correction for that. So with any microscope, whether it's a light microscope or an electron microscope, there are aberrations that we can account for, and then we can use that to do our processing. I'll skip this, but you have these slides on there. But there are different lens systems to not only focus and magnify, but we've made use of lenses to increase throughput. You can use lenses to increase throughput by doing something known as image beam shift. So back in the day when we first were using electron microscopes to do data collection, we would move the stage to a particular area and we would take an image. And it would take the goniometer, the stage of the microscope, a certain amount of time to settle. And what we can do is we can use the lens systems to image shift to a particular target and then beam shift back to the sensor. And what that has done is that has increased throughput quite a bit because it can take tens of seconds for the stage to settle, but it'll be only seconds for the beam to settle when you're doing some of these image beam shifts. So in reality, we can even get to over 10,000 images a day now with this, because with one stage movement, you can image shift a dozen microns, with some of the newer systems up to 20 microns away from the optical axis. And that has really increased throughput because you don't have to wait for a lot of this stage settling time. Unfortunately, this does introduce some additional aberrations, but our hardware and software can do some correction for that. So that's not only stigmation, there's coma, and there's defocus that can go off as you go further and further off the optical axis, and that's more of a correction that we can do in hardware.
What's the mount sample? I mean,
millirad. So, okay, so that's a typo. It's not.
sorry.
No. The good call. So it depends on how far you're tilting off the optical axis. So the more you do, the more aberrations that might come. So it's actually millirad. Some of the cameras have higher frame rate, and what that really means is then that our systems are collecting more and more data. So if we collect on the order of 10,000 images a day, and we have shorter exposures because our cameras are collecting faster, then we have quite a bit of data on the order of several terabytes. So that leads us to talking about detectors. We have different types of detectors that are scintillated, meaning they are photon converting. So we have electron hitting scintillator, kicking out a photon, then we convert that back to electrons, or direct sensing, like the cameras, CMOS cameras in your phone. So a lot of the early days when we were moving from film to initial cameras, there was CCD, and roughly about a decade ago, direct detectors became more mainstream. And that has really pushed the resolution forward because we don't have to do any of these conversions. So back in the day when we were using film, there was a particular type of grain size and there was a particular resolution regime that we could access. CCDs have a broader point spread function than direct detectors, especially CMOS direct detectors. Something that can happen with the scintillator is that when an electron hits a scintillator, you can have off-target effects, shot noise, and so that's really why we had such a large point spread function. Something to think about if you're looking at detectors, the MTF, the modulation transfer transform, is related to the sensor itself. And then we have something known as DQE, detector quantum efficiency. That's roughly the signal to noise of a sensor. So practically what that means would be every detector has a particular MTF, but the quantum efficiency can change depending on your flux. So if you have more and more flux, depending on your frame rate, you have a situation where you can have coincidence loss. And what that would mean is that the readout of the detector might be too slow and you have more than one electron event hitting that pixel. Though the DQE of a sensor is always better on lower fluxes because you have less coincidence loss. However, as you can see in the graph on the right, the frequencies are not uniform in terms of the readout. And so the way that certain detectors are manufactured, you may have better detection at higher and higher KUVs. And the reason for that is that what could happen is that your electron, if it's moving too slow, can interact with the sensor, and you could have secondary events. So there has been a big movement to try to get more sensitive detectors and lower KUVs. So that's why, if you notice, a lot of microscopes, a lot of data sets are collected at 200, 300 KUVs, is because our current generation of detectors are better around higher KUVs. To really underscore the difference between a CCD and a direct detector, this is an example of a real space image, but if you take a Fourier transform of this image, you can see that the Nyquist frequency for a direct detector goes further out than a CCD. And something that you're seeing is these rings. That's reflective of the contrast transfer function of the microscope. So these are the aberrations introduced by a microscope. There are a couple common detectors that you might see. The Gatan makes the K3. The K3 has a readout of somewhere around 1,500 frames per second. The terminology for K3, you might hear something known as counting versus counting super resolution. And what that means is then the detector will read out electron events per pixel, and it tries to normalize that. And something that we can make use of are super resolution techniques in light microscopy, in the sense that if an electron is hitting, let's say, the upper left quadrant of a pixel, and you can see the neighboring pixels, you can centroid that event to a particular quadrant. So what physically you might have in a sensor is 5,760 and by 4,096 in a typical K3 or maybe an Alpine camera. You can quadruple the pixels by virtually trying to centroid by quadrant. And that's where you can potentially go beyond Nyquist. So if you're collecting at a 1 angstrom per pixel size, so at a magnification where a pixel is 1 angstrom by 1 angstrom, if you're using super resolution techniques, you might be able to go below 2 angstroms. So if your pixel size is 1 angstrom, your resolution would be 2 nominally. But if you're using super resolution techniques and you have a very good sample, you can go beyond that Nyquist level. Something that has been introduced more recently is something known as correlated double sampling for your detector. And normally what you would do is you would have your sensor, you would reset the sensor, and then you would have an event and you would read it out. But what ends up happening is then your pixel might not reset necessarily to 0. And so what you can do is you can use half your frame rate to take a blank, as it were. So you can reset your pixel, have an event, reset your pixel, read it, have an event, and then read it out. And what that means is then that allows you to have a more sensitive electron event by your sensor. So, but you're using half your frame rate to do that. The other type of camera that you might notice by TFS is the Falcon. The Falcon has a little bit of a larger pixel. The K3 tends to have pixels on the order of 5 microns. Falcon is on the order of 14 microns. And something that is a little bit different would be it uses what's known as electron event representation. So instead of ahead of time thinking about, do you want to collect and counting or super res or particular frame rate, this particular readout allows you to have an XY coordinate over time. And then in software, after your experiment, you can decide whether you want what's known in Gatan as counting or super res, or you can specify your frame rate. So this is a little bit more of a flexible format in the sense that you don't necessarily have to decide ahead of time what your readout speed of the camera is. So some cameras would require you to specify what your frame rate is, what your pixel size is ahead of time, and some will allow you to do that after the experiment. So our detectors aren't really collecting single images. What they're really doing is they're collecting movies. And what that ends up being is that we can make use of that to account for the radiation damage of our sample, and we can do what's known as dose weighting. So here's an example of one frame from a movie, and as you build up the movie, you can get more and more signal to noise. And something that has been noticed is then that as we collect, the sample can move. And what we can do to gain resolution would be to do motion correction, where we align not just frame by frame, but patches of a frame together. And then we can also make use of the temporal resolution to know that as we add more and more dose, the contribution of each frame doesn't have to be equal. So for the early frames, we'll use the high resolution frequencies. And then as we collect more and more, then we'll dampen the contribution of the high resolution frequencies to our processing later on, because there's going to be radiation damage. Also with these movies, you don't have to necessarily do it by motion correction by frame or by patch. You can do it on a per particle level if you have enough signal to noise. So the end result when it's happening partly is that if you just take a static frame, so a lot of these older detectors, especially film, it will be one snapshot where you might have a lot of blur, but with a movie, whether you're using a CCD or one of these new direct detectors, you can do motion correction, and it's basically difference between the left side and the right side of the slide. Okay. So in terms of the resolution revolution, I just gave you a high-level overview that we had a lot of hardware developments, but we also had a lot of software developments to push our resolution forward. And we can have more of a discussion a little bit later, but in a particular microscope, just like a light microscope, it's highly configurable. So you can add different components, for example, phase plates, and you can have, let's say, post-column energy filters, et cetera. There's been a lot of studies for very common samples, what particular components of a microscope may help you push the resolution forward, and what may not necessarily do so much for typical samples. So that's really what I want to cover today, in the sense that the electron microscope has four main components. We have your electron source, you have a vacuum system, you have your lenses, and you have your detector. You'll be able to see a lot more of that this afternoon. And one advantage, again, with the practical is that you'll be in front of an electron microscope. You'll have an experienced operator, and given it's your sample, and if you want to play with it, you can also twiddle the knobs a little bit and do what you want. But with an electron microscope, we can access several different resolution regimes. I skip other types of microscopes. For example, you will get a vignette of a scanning electron microscope. That is also an electron microscope that's very useful. And with that, we can see how over the decades we've been able to use the electron microscope to interrogate a variety of samples, access a variety of resolution regimes, and be able to glean a lot of biological information. Okay. So I'll wrap up here for time, but does anyone have any questions on an electron microscope? Because what's going to happen next is Michael's going to talk a little bit more about running a facility and setting electron microscopes. Yes?
Is there any physical restraints that prevent the microscope from setting this direction instead of this direction?
There are electron microscopes that are more horizontal than vertical. There is the Hexi project at Diamond, where they'll build a lateral microscope. And I don't know, I guess space requirements, if we had a nice high tension tank, could we stack up an electron microscope? I don't know. That would be great for space saving. So you don't necessarily have to have an electron microscope vertical.
And also you mentioned there are like different detectors that can collect
Well, well, with the same sample, you can collect on different setups. Something that we have here is the ability to collect on an Alpine, a K3, a Falcon, with and without a filter, with and without a cold fig. And you can take the same grid and collect a small data set on all these microscopes, and you can see. If you have a very normal, typical sample, it's usually the sample that's limiting, because what you'll see is that you'll get very similar resolutions on a particular sample. If you have a very, very good test sample like apiferidin, you can start seeing the various differences. So if you want to compare the different detectors and different setups, you would want the same standard sample to go through. So for your question, what was it specifically?
No, I mean, my frame of reference is crystallography, and you can measure the signal to noise ratio of your spots and how far it different, things like that. I'm just curious if you can look at your image and have some parameter determine whether you like this detector more or that detector more.
I think that would be, well, in truth, for modern detectors and most microscopes, they're all really good, and you'll be able to reach the resolution you want. But if you want accurately to do that, you can calculate the MTF and DQE of each detector, and you can compare them, and they have differences. So there's a difference between theoretically what would be the best DQE and the best detector, and then practically in terms of when you're doing data collection. So we can run all sensors in a way that are very similar in terms of throughput and similar in terms of data quality. I think the best thing you can do is then you just go downstairs and just ask your operator, okay, can I run my sample on both microscopes so you can compare and contrast? So that's one difference here than other places. You might think what if I did this, what if I did that? We can do that here empirically. The reason why I'm couching is that it's really sample dependent, because on a test sample, we can get the same resolution on any setup, but most samples you're dealing with is not going to be apiferin. And again, we're not the Center for Apiferin Research. We just, we want to do real biology. Yep.
So what movies you are staying at the same plane, you are averaging all the way through the plane?
I didn't really go into it, but we have our sample fixed and our detector fixed typically during a data collection. There are certain motions, but yeah, it's in the same plane. You can account for that if your sample is doming because it's moving not just in X, Y, but in Z. You can do per frame defocus correction. That's not standardly done. Something that you might also, well, I didn't really go into, there's a free mean path of a couple hundred nanometers, and that's why we want the same sample. So all that is projected into the same plane. So there are different spherical aberrations that that you can sort of account for, that you're not projecting the same plane. There is situations when electron is hitting your sample inelastically, and it's either losing or gaining energy, and then it will project on a different plane. But we tend to, in the angstrom level, not really need to worry about that. You have to think about it. We have picometer wavelengths, and we can be several orders of magnitude pretty poor with our microscopy because we're really going after angstrom level data.
So the movie is really an average.
It's really an average. Well, because there's a particular frame rate, so we have to do some sort of binning. If we had more sensitive detectors and faster frame rate, then you could potentially do correction for the whole particle as it's moving. But we're doing an average over a certain temporal time. And that seems to be good enough for our purposes. Okay.